Without DNS, the internet wouldn't be very useful at all. Everything relies on DNS. You're using it right now. It's everywhere, but despite being everywhere, most people don't have a clue how it works. If they did, IT people wouldn't get away with blaming every problem on DNS. Honestly, it's like the IT equivalent of the dog ate my homework. Yeah, it's funny, we make memes and haikus about it, and sometime, somewhere, DNS really did eat someone's homework, maybe. But I've worked in IT for a couple of decades, and I've investigated a lot of supposed DNS issues. The root cause is almost never DNS, so we're going back to basics in this one, and I'm going to tell you how DNS works. First, what is DNS? DNS, the domain name system, is a way of storing bits of information and referencing it using a name. Other people can look up this information using that same name. It is most frequently used to look up IP addresses, and because of this, it is often described as the phone book of the internet. This is only one way of using it, and I'm not sure how many people these days actually know what a phone book is, but converting names to addresses is a good way to demonstrate DNS. If you're watching this on a computer, you probably type something like www.youtube.com into your browser. To your network, that is meaningless. Your computer cannot connect to that. It needs an IP address, but we squishy humans cannot remember the billions of IP addresses that make up the internet. www.youtube.com is a DNS name. We can remember it, and our computer can use it to look up the IP address for YouTube. When you type that into your browser, your computer sends a request to a DNS server, asking it to find the IP address for www.youtube.com. When it receives an answer, it connects to the IP address. This is why DNS is so critical for the internet to function. Computers deal with IP addresses, humans deal with names. Without DNS, our devices would never be able to figure out what we were asking them to connect to. It's also why DNS gets the blame for every problem. If your network goes down, the first thing to show a problem is typically DNS, because that's the first thing every device needs to talk to in order to find anything else. Someone always says, it might be a DNS issue, and then it sticks, because going back to tell people that, well, actually, the router was offline because Dave tripped over a power cable, that just invites further questions. I digress though. If you need to connect to DNS first, where is it? In a company, there's a good chance you have servers for this in a data center somewhere. At home, your router is probably your DNS server. That's what your devices connect to when they need to look up a DNS name. So does this mean that your router knows about every DNS name on the entire internet? No. The internet is massive, and the information in DNS changes constantly. Anyone can register a domain name and start creating their own DNS records. I can create one, and you need to be able to look it up. How does your router find my DNS records? One way would be to put it in a central registry somewhere, but that central registry would quickly become a bottleneck for the entire internet, not to mention a massive great vulnerability for everything. That simply wouldn't scale. So DNS is distributed. Nobody holds the full picture. There are thousands upon thousands of DNS servers all over the world, each handling their little piece of the puzzle. You can set one up at home and serve information about your domain to the rest of the internet if you want. Pretty much every registrar you'll buy a domain through provides public DNS hosting as a free service though, so I wouldn't, but you can. Let's say you did though. How would my device know to connect to your home server to find the records for your domain? The secret sauce is in the structure of DNS names. They are hierarchical, with the different levels in the hierarchy separated by dots. www.youtube.com. Actually, there is another dot. The very root of the hierarchy is represented by a dot, so written correctly, the address for this website should be www.youtube.com. All DNS names end in a dot, but most people don't realize that, and your computer doesn't expect you to, so it's treated as implied. Let's plot it out. The dot at the end is the root of the hierarchy. That has the child element, com. In DNS, we call this a top-level domain, or TLD, because it's the first level in the hierarchy after the root. Com is a child element, YouTube. YouTube is a child element, www. Looking at a single name, the hierarchy isn't obvious. As well as www.youtube.com, there was a mobile-optimized version, m.youtube.com. If we add that to the page here, M is also a child of youtube.com. Of course, there are other .coms like google.com, which is children like maps.google.com and images.google.com. There are other top-level domains such as .org, and it has children like Wikipedia, which itself has children like www, Commons, and Meta. Now we've added a few more names, the hierarchy is a bit easier to see. Let's get back to how your device uses this. Firstly, it's unlikely your device interacts with this hierarchy directly. As I said, it will send its query to a DNS server, likely your router. Your home router probably doesn't work with the hierarchy directly either. Instead, it probably acts as a forwarding server and simply passes the query on to another DNS server operated by your internet provider. That DNS server is the one that actually resolves the query, doing so in a recursive manner. Here's how it works. We'll assume the DNS server has no knowledge of the hierarchy starting out, so where does it begin? Each DNS resolving server has at least a list of root servers it can use. These DNS servers are responsible for the root node in the hierarchy. They are well-known servers operated by several organizations around the world and overseen by the Internet Assigned Numbers Authority. This is the starting point. These root servers don't know about every domain in the hierarchy, they only know about their direct children. In the case of the root servers, their direct children are the top-level domains. This is how DNS decentralization works. An authoritative DNS server knows about and can provide records for its immediate children. So our fictional resolver starts with one of the root servers. We can't ask the root server about www.youtube.com, it doesn't know about that. We can ask it who is responsible for .com though, because .com is a child of the root. The root server gives us the address of a DNS server that is responsible for .com, and we ask it. It also does not know about www.youtube.com, because it's not one of its children either, but youtube.com is. So the .com DNS server gives us the address for the youtube.com DNS server to ask next. This time www is the child, so we can ask the youtube.com DNS server for the IP address of www.youtube.com, and it gives us the answer. This is how DNS names get resolved. Your DNS server starts at the root and works its way down. If each node in the hierarchy knows about its own children, it can pass you on to the next step until you've worked your way down to the server that has the answer. Now, I mentioned your router doesn't do this directly and likely forwards on the query to another server. Why? The answer is caching. You see, your devices need to resolve DNS names constantly. If we had to go through this entire recursive process every time, it would have a significant performance impact, both to your individual devices as well as the internet's DNS infrastructure. Instead, DNS servers and individual devices remember answers. That's what caching means, remembering previous answers. When you browse YouTube, your computer needs to resolve www.youtube.com for every request your browser makes. Every page, every script, every image, every video. The first time this happens, it has to ask DNS. The second time, your computer will have remembered the answer, saving precious milliseconds. Modern web browsers actually cache the result as well, so the operating system remembers the answer, but so does your browser, shaving off another valuable millisecond or two because the browser doesn't have to ask Windows to resolve the name. Other operating systems are available. This caching happens at every level through the chain. Your router remembers the answer as well, so if another device in your network needs to resolve www.youtube.com, your router can return the answer without forwarding the query out to your internet provider. If another customer of your internet provider wants to browse YouTube, your internet provider's DNS server has remembered the answer from when you asked, and it can respond to that other customer without going out to the root server and starting the whole recursive process. Caching is good. It speeds things up and reduces network load, but we can't do it forever. DNS records change, so if we just remembered every previous answer, they'd eventually all be wrong. Caching is time limited, using a value called TTL, time to live. TTL is a setting on every DNS record that advises how long the response should be cached for. It is advisory. In an ideal world, everything would obey the TTL, but you can't enforce it. And I've had issues in the past with mobile operators choosing to ignore the TTL and just caching everything for 48 hours regardless. Most servers and devices do respect TTL though. When choosing a TTL value for your records, it should be based on how frequently you expect the record to change. If a record is expected to change all the time, such as one that is generated dynamically based on a device's current location, you may set it to a few minutes to ensure that you're always getting the latest version. If a record is very unlikely to change, like say the name server records for a domain itself, then you might set it to a couple of days. The lower the TTL, the more quickly it can be updated, but the less benefit you get from caching. A higher TTL is slow to update, but it'll usually resolve from cache meaning you don't need to wait for a full recursive resolution. This idea of TTL and caching is important to understand even if you don't operate a DNS server yourself, because it changes the way your devices find services on a network. If a DNS record changes and you have the old one cached, you'll be connecting to the wrong address. Some networks may provide different answers to the same DNS query in order to direct your device in the most efficient route. For example, if you look up a google.com server in France, you'll be pointed to a Google server located in Europe, whereas if you run the same query in the US, that would direct you to a US-based Google server. If the service you're connecting to is internal, your local DNS server might give you its local IP address, which avoids the need to go out to the internet at all, but won't work from outside that network. Connecting a VPN changes the network you're connected to, so using a VPN can cause all sorts of strange DNS responses to be cached. It's important to know that different levels of caching exist. On Windows, you can clear your operating system's DNS cache by typing ipconfig/flushdns at a command prompt. This will cause Windows to forget any DNS responses it has previously remembered. But if your browser has also cached them, it won't make any difference until you restart your browser as well. Conversely, if you restart your browser without clearing the Windows DNS cache, your browser will just get the old record again from Windows. If a DNS record has changed, that may be cached somewhere upstream as well, so clearing the caches in your browser and your operating system may not have the desired effect if your DNS server responds with a record from its cache. Understanding the different steps will help you figure out where problems may be creeping in so you can better troubleshoot them. A little hint if you're using Windows. The NSLOOKUP tool is used to resolve DNS records using the Windows command line. If you type setdebug, it'll provide a lot more information, including the remaining cache TTL of the record so you can see when it's going to expire. Now you understand how name resolution works and where caching fits in, the other common confusion comes from the different types of record. DNS is not just used for IP addresses, even if that is one of the most common uses of it. I'll find a list link in the video description, but there's something like close to 50 different record types, and roughly double that if you include obsolete ones. The good news is that even most IT folks will only ever have to deal with a handful of these types, so let's cover the common ones that you might actually need to know about. First we have the A record, sometimes called a host record, although the A actually stands for address. This is the big one. The A record is where you record an IP address. This converts DNS names into something your computer can actually use. Closely related is the AAAA record. The difference between an A record and a quad A record is the A returns an IPv4 address and the quad A returns an IPv6 address. IPv6 addresses are 4 times the size of IPv4, so 4 A's. Next you have the CNAME, sometimes called an alias, although the C in CNAME stands for canonical name. Instead of referencing an IP address, the CNAME references another DNS record. That means, same as that guy. You might use that if you have a bunch of names that resolve to the same place, so if you need to change you can update one and have the rest follow. It's particularly useful if you use a service hosted by a third party, because you can create a CNAME in your domain that references an A record in their domain, and they can keep it up to date instead of having to coordinate with you every time an IP address changes. www.youtube.com is in fact a CNAME that references a google.com DNS record. Another rather important record is the MX record, short for mail exchanger. Have you ever wondered when you click send in an email how your provider knows where to send it? Although email is becoming increasingly centralized with a handful of providers, anyone can set up their own mail server, and the rest of the internet needs to know how to find it. That's where the MX records come in. If you need to know where to send an email, you look up the MX records for the bit after the @ sign in the email address. The MX records will list the receiving servers for that domain with a priority order. The next most common type of record is the TXT record. As you may have guessed from the name, this stores text. What kind of text? Well, anything really. It's commonly used by SPF and DMARC to store policies, and DKIM to store cryptographic keys. Cloud providers will often ask you to put some information into a TXT record to prove you own a domain. They're very versatile. In fact, that versatility has made some other record types obsolete. Another type of record you may need to know about is the NS or name server record. You won't touch these all that often, but they are very important. The NS record tells the internet what DNS servers are responsible for a domain. That's how when you're working your way down the hierarchy to resolve a name, the layer above is able to pass you to the next server. It's using NS records to locate it. If you wanted to host your own DNS server at home, again, that's not a recommendation, you would instruct the rest of the internet to use your home server to resolve those names by updating your domain's NS records to reference your home server. Typically for a public domain, you would update these to your registrar because they'll be hosted by whoever manages your TLD. You can create your own NS records to further delegate subdomains though. For example, if I wanted to give you control of the subdomain youtube.protectshow.com so you could create records like media.youtube.protectshow.com or rickroll.youtube.protectshow.com, but you couldn't create something under protectshow.com itself, I could add an NS record for youtube.protectshow.com that referenced your DNS provider, and that would tell the internet that you were the authoritative source for anything.youtube.protectshow.com. I'm not going to do that, maybe one day, but for now you'll have to be satisfied with the comments section. Those are probably the main DNS record types that you may come into contact with. A few others you might come across. SRV records are used for service discovery. They're often used by directory, voice, and messaging services. You'll probably run into them if you manage a business network, but they're usually pretty application specific. CAA records restrict which certificate authorities are authorized to issue certificates for your domain. SOA is start of authority, which you don't generally need to worry about unless you're setting up replication or trying to get in contact with someone about the DNS zone, but there are usually easier ways to do that. I'll link the full list, but really this is probably more than most people will ever use already. So now you're all prepped. You won't go causing any DNS issues, will you? And the next time an outage gets blamed on DNS, feel free to ask them why DNS wasn't working. Was there actually a problem with DNS itself, or did someone just need to plug a network cable back in? If the answer isn't satisfactory, refer them to this video. As for you, your next one is right here. Thanks for watching, see you next time.